The topic of this presentation is fatigue lifetime of glass fiber reinforced polymer laminates in critical plane defined by equivalent normal stress. The authors of this presentation are Karolina Głowacka, who is me, and Tadeusz Łagoda. We are from Apollo University of Technology at Faculty of Mechanical Engineering, and our university is located in Poland. In my presentation, I will start with a few words about multi-axial fatigue criteria in plane stress state. Then we will present the results of fatigue tests of glass fiber reinforced polymer laminates with a code presented on the presentation in here. Then we will apply the multi-axial fatigue criterion in the critical plane for this type of composite, and next we will verify it and we will compare it to the other existing ones. And at the end of the presentation there will be a few conclusions which we have found. First of all, I will say which notation we are going to use, because there are different notations which we can use talking about stress. The standard notation is on the left and the Voigt notation is on the right. For composite materials we usually use the Voigt notation, which is why we thought that it would be useful to show this table where you can see which stress in the standard notation is which stress in Voigt's notation. As we are going to talk just about stress and just in plane stress state, just these three bolded data are most important. When we say about fatigue criteria, there are many of them. But we thought that we could start with some popular strength criteria which are used in the statics and analyze them for fatigue lifetime. First, for the statics, the most popular strength criteria are, according to data literature, the most popular is the criterion of maximum strain. Then we have maximum stress, and next we have a criterion proposed by Azid, Tsai, Hill. Actually, they weren't specifically working together on this criterion, but they managed to use one and another's work to figure out a really useful criterion. Then we also have the Tsai-Hill criterion and many others, but the presented ones were the most important for us just to begin with it. On the right, you can see the Azid-Tsai-Hill criterion, which in plane stress state has a form of the equation presented here at the top. Then we also thought that we could analyze the Norris criterion. This is a very similar criterion to the Azid-Tsai-Hill. Perhaps it's not as popular as the Azid-Tsai-Hill, maybe because it was presented for in the case of wood and not a typical composite material. However, it is often used, and sometimes even people use the Norris criterion and call it the Azid-Tsai-Hill. The difference is just in one place in this equation, as you may see it in here. We chose those two criteria and we analyzed them. Just to be able to compare the criteria, we decided to define the equivalent stress. The equation have been already used and showed the satisfactory results. So this is how we could analyze it and to be able to compare the equivalent stress with the normal stress, with the normal stress in the direction 1. This is the stress we were comparing it with. So for Azid-Tsai-Hill criterion we have on the top, and for the Norris criterion we have it on the bottom of this page of this slide. And the tested specimens It's not the test we have conducted. We use the information, the data in the article, actually 2 articles presented by Philippidis and Vasilopoulos, and we use the data which they have presented. These were the glass fiber reinforced polymer laminates with a coat at the left. On the right you can see a shim. Of course it's not the whole material, we should give it twice, yeah, so this is a symmetrical shim. We should give, that's what on this page, we should do it like twice, yeah, so then we would have the laminate, but in general we wanted just to show in which direction we would have 0, as we were using then the angles theta, which were compared to this 0 direction. So the most important thing which you can see in this photo, in this figure, is it's the axis which we are comparing to the angles, as we use the data for different angles of cutting. We had 0 degrees, 30, 45, 60 and 90, and we were analyzing those 5 angles. The stress in each direction can be recorded depending on the angle of cutting the specimens, and to record it in this way we use these 3 equations here at the top left of this slide. And based on the results taken from the literature, for the cycle asymmetry coefficient R minus 1, the fatigue characteristics were determined in accordance with the Baskin proposal in a double logarithmic system. And this Baskin's equation is presented on the left bottom of this slide. Using the data, we were able to determine the coefficients used in the Baskin's equation, and for each angle of cutting specimen, we presented it in this table on the right. We used, in all of the cases, we used the number of cycles 10 to the power of 5. Of course, some data were for more cycles, but to have comparable data, we used in all of the examples the 10 to the power of 5 number of cycles. As we knew that we need to know the maximum stress in each direction. Yeah, so it would be the x would be the strength in the longitudinal direction, y would be in the transverse one, and s would be strength for shearing the material. As you can see, the x and the y were taken from the for the experimental test, also presented in the article. However, in the case of the S, we were analyzing the tension of the material at angle 45 degrees, as it's an often used practice. However, then you have to divide it by 2.2 to obtain the shearing strength. Theoretically, in the standard, it is written to divide it by 2. However, in the article, they also proposed that if you want to analyze how strong the material is for shearing, you should divide this strength in the 45 degrees cutting specimen times divided by 2.2. As you can see, we wanted to remind you how look the equations for equivalent stress in the Ezit-Sahil and the Norris equations. You can see that apart from the stress, there are some constants. For example, x divided by y and x divided by s, and this is why we just calculated these coefficients, and they are calculated at the left bottom of this slide. as they were used later in the analysis. The criteria which have been up to now presented, acid, Hill, and the Norris criterion, are useful, and they are used with positive response. However, due to the fact that they are non-linear, they cannot be applied to non-proportional loads, for example. So there was a proposition to apply a linear relationship for the components in the form of equivalent normal stress, however in the critical plane. Of course, the critical plane is not a plane which would be the plane of cutting or something, the plane of how the damage appears. This is a fictional plane where we analyze the maximum normal stress. And in other articles it has been already presented with the equation here at the top of this one. However, this equation has been presented for metal material, which is then an isotropic one, of course, and the composite materials are anisotropic. This is why sometimes we can't straightly use them. After some analysis of the results, we have found out that if instead of dividing the last component by 2, if we divided it by 4, we would have better results. So this is an empirically tangent equation. We've found out that it could be a good solution to divide it by 4. After using this criterion, we have determined the angles of the critical plane, as we had to define where this critical plane would be. And we have found out that there is a relationship between the angle at which the specimen has been cut out and the angle of this critical plane. As you can see, this is an exponential function, which relationship is written at the left top. It's not linear, but almost. And this relationship can be easily seen on the graph. However, we had some idea, some analysis, but we had to find out if our suggestion is good. So first of all, we use the acid-Hill hypothesis, and here you can see the relationship between the calculated equivalent stress for different number of cycles to failure, and it has been calculated for each theta. So this is the angle of cutting the specimen, and they are depending on the color used, there are different angles. For the acid-Hill criterion, you can see that the green triangles, which is the 45 degrees, were calculated to be higher than the 0 degree. Yeah, because we were comparing everything to the 0 degree, as there the results seem to be the most comparable. So the 45 degrees gave higher results of the equivalent stress for the acid-Hill criterion. Here there is exactly the same analysis has been done, but it's for the Norris hypothesis. And here you can see a very similar solution. Also for the case of the 45 degrees, the obtained results were a little bit too high. And in this case, we have our proposition, which is defined in the plane of maximum normal stress, which would be the critical plane. And it's in this case, you can see that the 45 degree cut specimen gave great results. However, we had problem with the theta equal to 30 degrees. In this case, the results were a little bit too low, so it also wasn't so perfect. However, just if you see the results, it may not be enough, as based on the graph, you can see that they were good, all of them were good, but not perfect. So we decided to determine the dispersion of the results using the equations which we have had, the equations which are shown on the left of this slide, and we used them to calculate the dispersion. And we have found that in this table you can see the results, and when the value is lower, closer to 1, then the better it is, and when it's bigger, then it's worse. So as you can see, the acid-Say-Hill criterion gave the worst results, as here we had 1.142, and for the Norris criterion we had 1.067. So the acid-Say-Hill criterion appears to be much worse than the Norris criterion. This is also why we wanted to use the Norris criterion to show that even though acid-Say-Hill criterion is more popular, sometimes the Norris criterion appears to give more satisfactory results. However, what we most wanted to show and to analyze was the new criterion defined in the critical plane. And in this case, we had 1.130. So, well, to be honest, we can see that the Norris criterion appeared to be better than this one. But our proposition was still better than the acid-Say-Hill suggestion. So it's not perfect, but it's already good and gives really good results. So maybe let's go on to conclusions. As I have already said, the application of the acid-Say-Hill criterion for this type of the laminate gave the worst components of the results, and on the other hand, the Norris criterion appeared to be the best. And as I have said, the newly proposed criterion, which was our new suggestion in the critical plane, also gave satisfactory results. However, there is the third point in these conclusions which I haven't mentioned before, because the newly proposed criterion gives us new possibilities. And as I have already said in the introduction, it has a very big new possibility, as it can be used in complex operational or non-proportional load states. So in the future, we would like to analyze if for such states it would be useful as well, as it gives us a possibility to be really good and give us new possibilities. So we hope that in the future we could use this criterion for new applications.